Hello and welcome back to Jules Bench. Again, my name is Greg Perugini, and today we're going to be talking about circuits and Kirchhoff's laws. Now, if you remember, in our previous lab, we took a look at both parallel circuits and series circuits. When we have a series circuit, of course, we're connecting up end to end, and it's very easy. We just add them together. In parallel, we have to do a little bit more complicated of a calculation. But in this lab, we're going to do a combination of both of those. You'll need much the same equipment as we had in the previous lab. Now, I've done some of the calculations already for you, so I'll be reading off of this sheet, but I'll also give you this sheet as an image on the labs. But let's start with this simple circuit. We have parallel connections, and we have those being in series with the 80 ohm. So first we must reduce this parallel part to its equivalent resistance, and then add that to the 80 ohm. So what would the total resistance in this circuit be? Well, for the parallel part, it's 1 over each of the resistance, 1 over 100 and 1 over 50, to get the equivalent, and the equivalent being, in this case, about 33.3 ohms. We then simply treat that as a series portion and add that to the 80, giving us the total ohms of this circuit as being 113.333 ohms. So let's take a look at this circuit. Let's assume that this is a 1.5 volt battery here. That voltage is going to give you, of course, 1.5 volts, and we already figured out what the current would be, about 13.22 milliamps. We can get that by doing I equals V over R. Current is equal voltage over resistance. So the voltage being, in this case, a 1.5 volt bulb, and we got the current by just simply taking the total resistance and dividing it, okay, the total resistance, taking that 1.5, dividing it by the total resistance, giving us the current, which I said is about 13.2 milliamps. When we go into this resistor, that resistor is going to reduce the voltage. Again, we can tell you how much it will reduce the voltage because the current is going to stay the same in the series part, and we know the resistance being 80. So the current being 13.2 milliamps divided by, or is equal to V over 80, well, that can give us the voltage drop. And taking that voltage drop, okay, so that voltage drop being about 1.056 volts dropped by that resistor, we come out of it at this point at roughly about 0.444 volts. Still have the same current. Current's the same in that series portion. The current being, of course, what we calculated before as 13.2 milliamps. So now we hit this junction. So at this junction we have to split. How much we split depends upon the resistors on each side. In this junction, we could do this, I equal V over R, Ohm's law, and take that 4.44 milliamps equals the volts over 100, and I get a that 40.444 volts over 100 gives me a 4.44 milliamp amperage into this junction. Again, I'll give you the sheet of paper that'll explain a little better. Then into this junction, much the same way, I equals V over R, the V being 0.444 going in, divided by 50, giving us an 8.88 milliamps into this. Bottom line is the milliamps here, 13.2, gets split between this one, which is gets split to 4.44 milliamps this way and 8.88 milliamps this way. Now, of course, these two will reduce the voltage because they're resisting. And what we end up with coming out of both of these, your calculation should show that we would reduce the voltage to 0 in this one and 0 in this one. Both of the currents, this one and this one, combining again. So at this point, what we would have is the combination of the two amperages, 4.44 milliamp and 8.88 milliamp, added together to give us the 13.2 milliamps that we started from, and 0 volts, which we should expect going into the opposite side of the battery. Again, I will give you this whole sheet as a JPEG in the Blackboard. So, in summary, in a series circuit, the current is the same in all places in the series circuit, and the voltage gets reduced as we go from plus to minus. So we started with a total voltage at the positive side, and each resistor reducing the voltage. By the time we come around to the opposite pole, we should have a voltage of 0, as I showed in our example. In this parallel part, the voltage is the same in both of these, but the current is reduced to on each leg going in. And that's just another way to state the loop law, Kirchhoff's loop law. Both of these legs must add up to give you the current as we would expect in a series, and it must be split equally like a river flowing in. Each portion, depending upon the resistance, must add up to the whole, both going in and coming out. In a way, it's nothing more than a statement of conservation of energy, conservation of current. So for this lab, number one, take 3 resistors, tie 2 of them together. And what I mean by tie 2 of them together is to simply take the ends and tie them together like that, and that's your parallel circuit. And then connect it up to a 3rd resistor, and then calculate the amount of ohms that you should have, and you're going to verify this with your multimeter. The second part is you're going to hook up a battery into this and verify the current, much like I did walking through the circuit, at 3 different places. First place is fairly easy. You figured out all the ohmage that this parallel and series circuit gives you. Once you have the ohmage and you have the volts, it's not hard to figure out the current for that particular part. Do it for 2 other parts, verifying Kirchhoff's loop law. So, for each of those, whether you're using the battery and the test through, I need 2 pictures, 1 for each test. I want you to verify those with Ohm's law and Kirchhoff's loop law and show the work. Be complete with your methodology. I've been seeing some methodologies that are a little bit light. Be very detailed in your methodology. Assume the grader knows nothing. And good luck.